Welcome back to another episode in this series as we try build a flight sim in Minecraft. Last time, we spent some time figuring out how wireless redstone works, after it became clear that regular data lines weren't going to be feasible for this project. This time, we'll take these concepts and refine them a bit to build our wireless receiver, which will attach to the main screen. By the end of the episode, we should have receivers set up for all the pixels, which we can test to make sure this concept works properly. Once that's done, it'll set us up for creating the transmitters so we can actually stream the different flight paths for our flight sim to the screen. There's a few things we've got to figure out before we start building. First, we need to determine the rate at which this dropper trapdoor mechanism can reliably receive data packets. Since the screen runs on 8 game ticks, I need to see how many individual receivers I need for each pixel. I already noticed that 8 game ticks is too fast for a single, so you can see here if I run it on this clock, some of the items just don't have enough time to drop down. Okay, let's try 16 ticks. Looks better, but if we run it for a bit, it's still not reliable 100%. Okay, 24 ticks. I have to do it in multiples of 8. Let's let this run for a while. Alright, I let it run for a minute and didn't get any buttons getting stuck, so looks like we need 3 receivers per pixel. Next, we've got to figure out how to join the output of these 3 receivers and split it vertically into 4 different signals, since our wiring layout is vertical for each pixel. I really want to stay away from redstone wire as much as possible, since these things are going to be firing a lot and there'll be a lot of them, so any lag I can mitigate at this point will have an exponential impact on the final machine. I think I'll use slime blocks. I think this is the best option for merging and distributing the signals. So it'll kind of look like this going down. And then if need be, I can use an extender here to make the signal go down further. I also want to rig this whole thing with minimal delay, so the closer to instant I can make it, the more responsive the machine will be at the end. Okay, now we've got to figure out how to read whether a signal comes at the first, second, third, or fourth tick of a cycle. I think I'll do that by having 4 clocks per receiver and then compare when a tick aligns with a clock pulse. The clocks will all be offset by 1 tick, and that should give me the ability to separate out the pulses. Okay, I spent some time on this, and here's what I came up with. So what'll happen is when this observer is triggered, it'll pulse this redstone wire, which was the only wire I couldn't figure out how to get rid of, but just one wire, so that's okay. And the wire will be pulsed only 1 tick. And if that tick happens to line up with this block being here, which is also only here for 1 tick, then it should send power to the repeater behind it. I'll have to figure out how to get the signal out of the machine at the end, but I'll do that later once I know better what the full receiver is going to look like. Okay, one last thing I need to know before building this thing is we need to know how many blocks of space we need to make a protocol that allows us to receive signals for 15 pixels in 1 tick. The formula for this is 2n plus 1, which is 31 different update orders, and the shorter I can make these the better, so let me play around with that for a bit. Alright, here it is. I'm using comparators, observers, repeaters set at 1, 2, 3, or 4 ticks, wire, and blocks. These all have a different impact on the update ordering. So I can demonstrate what I mean by building this little motor here. And now what should happen if these are all in the correct order is that this little engine should travel all the way down this line and not break. So let me start this. And we can see it goes all the way down the line. If I pause the game and step forward, you'll notice that these repeaters all light up in the same tick. So the update order is the only thing that controls whether this machine moves forward or stops. And all of these are unique orderings, so no matter how I mix and match any 2 of these, as long as they're in this order, they'll always send the update the correct way. So if I were to break this sequence by, for instance, reversing these 2, and now run it, You'll notice it stops here because the order was backwards. So testing this all the way through, we see that the machine works for the entire line, so we have 31 unique update orders that we can now use for our receivers. And now if we look at the amount of blocks required, we see it's 4 blocks of space. So now that we have that info, we should be able to put all this together and build our first receiver. Let's go. Okay, here it is, our first receiver. So I put all the pieces together. These pink wool here is where the update orders will be defined. And over here, you see I've got 3 individual receivers, and they cycle through at a 24 game tick rate. Then the slime blocks extend down to send the signal downwards, and the signal merges with these observers through these blocks and into this one lone wire. So I ended up building 8 clocks, set up in a way that I can split out a single pulse from a 4 pulse duration. So based on whether the detector item was in the first, second, third, or fourth position in the chain, it'll send an output to the respective repeater since these clocks will all be started 1 tick apart. Okay, now we've got to figure out how to get this signal out of the machine. I want to get the signal out of the machine and normalized at the same time, meaning no matter what signal comes out, they'll all sync up across the whole machine. Since each receiver has 4 outputs, and I'll have 7 of them vertically, I need to have 7 plus 3 is 10 different output timings total. To show what I mean, let me build up a wall of these receivers, which is how they'll look at the end when they're all tied to the screen. Okay, here we have it. There's a wall of 15 wide and 7 high receivers, giving us 28 output lines on each vertical. Since each row of pixels will be offset by 1 tick, I need to normalize the output by having 10 different timings for the output lines. So remember, this is our output, and I think I'll try bring it through here. All right, let me build those up real quick. Here we go. Took some doing to make them work in this precise shape so they don't interfere with the receivers themselves. So if I power them all at the same time, you'll see that they repeat the output 1 tick apart. Okay, now to bring this all together with the receiver, and then we'll run some tests. And here it is. Everything's merged together now. So let's do some testing to see how this actually works. To start the whole machine, I just tap this note block, and if we step back, we should see this startup sequence kind of propagate through the whole wall. I built this in a way that all the clocks start at the precise timing required to receive their respective wireless signal. So depending on which pixel they're responsible for, they'll start up in that sequence. Okay, it's all started up. And to test, I've just put command blocks here that spawn a different color wool on that makeshift screen over there. So right now the screen is essentially displaying static, this changing 2-color pattern. That's because I'm not currently sending any data for it to receive. But I can test that it's working by dispensing an item into my inventory like this, and it should do a phase shift for the whole screen so that the colors switch. That works nice. Something I noticed is that there seems to be some location-based interference. So you can see if I move closer to the machine and watch the screen, you'll notice that the pattern kind of gets disrupted as I get into the range of some of the receivers. So when we attach this to our screen, we'll have to keep this in mind and put them at a safe distance from the player. All right, that'll do it for today. Next time, we'll work to connect all this up to the actual screen, and then we should be able to display whatever the receivers are receiving on our actual shulker box screen. Thanks a lot for watching. See you guys next time.